So we've reached the back end of this course, and we're going to circle back, as I anticipated, to oscillations and waves. We're going to put some more mathematical framework behind these concepts. So first we're going to start by talking again about single coordinate oscillations, that is a single thing that is vibrating. And then we're going to talk about forces that drive oscillations, because so far we've considered an oscillation that is already going and an oscillation that is being damped out, but we haven't talked about something that can kick these oscillations off to begin with. Then we're going to talk about coupled oscillators, where we can have multiple oscillators that can exchange energy, and we get some really rich and interesting behavior that emerges from systems of coupled oscillators. We're going to talk about using Euler-Lagrange equations to solve systems of coupled oscillators, because it's a really great way of attacking these problems. And then using coupled oscillators, I mentioned we have emergent physics, and one of the things that emerges from a system of coupled oscillators as you keep adding more and more and more coupled oscillators is we get waves and the wave equation. And then we can talk about properties of waves that emerge from this kind of mathematical treatment. So just again to motivate and introduce this topic, we're talking about wiggles, and mathematically speaking, wiggles are things that we represent using complex exponentials e to the I omega t and or e to the I kx. Now omega is a frequency, it's radians per second, and k is also a frequency, it's radians per meter. So omega and k play kind of the same role. When we have just oscillations in time, we have something like a simple harmonic oscillator. If we add oscillations in space, then we get waves. So by looking at examples of oscillators, what we hope to understand and appreciate is just how universal vibrations are in physics. And that's something that I really hope that you take away from this course, is just how often we bump into things that vibrate. Examples of things that oscillate, just to give you some range of time scales that we're talking about here, like on a very long time scale, this is an oscillation of the sun, and we talked about modes. This is a mode of vibration of the sun. It looks kind of like a liquid drop vibrating like this. It's got a frequency, this particular solar oscillation has a frequency of 10 to the minus 4 hertz. This is an oscillation we can represent using an equation for simple harmonic motion like the one we've already met. This is another example. It's they're silver nanoparticles. These are little particles of metal, and we shine light on them. The electromagnetic radiation, which goes at around 10 to the 14 hertz, or 6 by 10 to the 14 hertz, causes the electrons to vibrate backwards and forwards. We drive these electrons. They oscillate, this time with a frequency that is some 10 to the 18 times faster than the solar oscillation. Faster still, we have nuclear vibrations. These go around 10 to the 20 hertz, and these are kind of like liquid drops as well. We talk about the liquid drop model of the nucleus, which is kind of amazing in the sense that, these liquid drops kind of look like the oscillation of the sun, but the difference in timescale here is about 10 to the power of 24. So really huge variations, but very similar physics underlying some of these things. Now, the rest of the slides I'm just going to flick through, because this is revision from material we did at the beginning of my section. So remember, we talked about undamped simple harmonic motion, and we wrote down a differential equation, we solved it, and we have some sinusoidal solution, or a solution in terms of complex exponentials. Then we talked about the energy contained in an oscillator, so we talked about it being broken down into kinetic and potential, and we had equations for the total amount of energy. And then following on from this is a whole bunch of mathematical revision in terms of phasors and trigonometric functions and complex exponentials and real and imaginary parts. This is kind of revision, and for your reference, it'll appear in the PDF notes on the edX page, but I'm not going to go through it in this video.